Hello everyone. Welcome to Week 9, Quality Management. This week, we transition into a core area of operations management that dictates long-term success, ensuring that our products and services consistently meet and exceed expectations. We'll be focusing on the key concepts, metrics, and systematic approaches used to achieve high quality. By the end of this chapter, we aim for you to grasp several critical distinctions and methodologies. You should be able to clearly understand the difference between design quality and conformance quality. We will also explore the contrasting impacts of internal and external failure costs. Crucially, we will examine the relationship between process variation, specification limits, defects, and overall process capability. Finally, we will introduce the systematic process used to achieve continuous quality improvement, and briefly touch upon key topics such as robust design and Six Sigma. When defining quality, we start with two fundamental components. The first is design quality. This type of quality is inherent and embedded directly into the design specifications of the product or service itself. Strategic questions addressed here include whether the design effectively satisfies customer needs, and how the design compares competitively to what rivals offer. Think of this as making sure you are designing the right thing. The second component is conformance quality. While design quality focuses on the blueprint, conformance quality focuses on execution. It depends entirely on your production and delivery processes, your operations. The central question for conformance quality is, does the process output actually match the established design specifications? This directly addresses how many defects are being produced. To demonstrate why conformance quality matters so deeply, let's consider a common scenario. Imagine you are the manager of a tire plant. Through testing done at the end of the production process, you discover that, on average, one batch out of every 100 used for the tires does not match the strict design specifications. This seems rare. Only 1% of batches. When you find one of these bad batches, you immediately have to scrap approximately 40 tires. Then spend time and labor to remix that batch of rubber compound. Based on your initial calculations, you estimate the combined scrap and rework costs are very small, less than 0.05% of the cost of goods sold. You might feel this problem is under control, perhaps reasoning that preventing this rare issue would cost more than tolerating it. However, this perspective often dramatically underestimates the true total impact of defects. Imagine a mobile phone made of 100 separate parts. Each part has a 1% defect rate, meaning there is a 99% probability of it working properly. If all 100 parts need to work for the phone to function, what is the probability that the finished phone will work? This concept applies across complex operations, whether manufacturing cars or computers, or delivering multi-component services like healthcare or hospitality. The impact of non-conformance can appear at various points. At a specific process step, at a bottleneck, at the end of process, or, worst of all, in the market. The crucial insight here is that the cost of a defect depends heavily on where it is detected. If a defect is found early, say at a process step, the cost might primarily involve lost labor and materials. If the defect makes it past the bottleneck or to the end of the process before detection, the costs increase. If the process is capacity constrained, these costs can also include lost sales revenue. This is known as internal failure costs. If a defect slips past your internal inspection points and reaches the customer, the market, costs escalate dramatically, moving into the realm of external failure costs. These are financially devastating, including lost reputation, liability costs, recall expenses, and warranty costs. Ultimately, defects impact the financial health of the organization. This diagram illustrates how defects systematically erode ROIC, return on invested capital. By attacking its core components, defects increase the cost element, both material and labor. They reduce revenue by negatively impacting the volume and the percentage of demand fulfilled. Furthermore, defects often increase the requirement for invested capital by affecting working capital, fixed capital, and inventory turns. By lowering margin and potentially increasing the capital required, defects significantly diminish the overall financial return. Imagine a simple production line, consisting of several key steps. Step 1, Step 2, Step 3, and culminating in the final product. Each step has its own designated tasks and personnel, all working harmoniously to meet demand. On a day when everything goes as planned, the flow is seamless. In Step 1, raw materials are transformed into components. Next, in Step 2, these components are refined. By the time they reach Step 3, they are nearly ready for assembly into the final product. Here, the labor costs are predictable, and material usage is efficient. This steady flow meets production targets, satisfying customer demand. Now consider what happens when defects creep into this well-oiled machine. In Step 1, perhaps a piece of machinery malfunctions, producing substandard components. This triggers a chain reaction. Once the defective components reach Step 2, they cannot be processed as intended. Here, workers are forced into rework, undoing their previous efforts and draining time and resources. Thus, in manufacturing, internal defect rates don't just impact the immediate step. They create a ripple effect that can hinder the entire process flow. Scraps and rework dramatically influence capacity, requiring more labor and materials than initially anticipated. Imagine a scenario where a faulty component is discovered during the final quality check. The cost implications are staggering. Not only has time been wasted, but the company also faces the burden of reworking a batch of products. However, if the defect had been caught earlier, a simple misalignment in the assembly, this would have allowed the team to rectify the issue without impacting the entire production. By integrating early detection methods, capacity can increase significantly. For instance, when defects are identified in the initial stages, production flow remains uninterrupted, allowing teams to allocate resources efficiently and maximize output. A factory that detects 90% of its defects in the early stages may find its production rate surging by 20%. This will not happen for a factory that only identifies problems at the end. By fostering a culture that emphasizes attention to detail and prompt identification of problems, businesses can enhance efficiency, reduce costs, and ultimately improve customer satisfaction. As demonstrated through the lens of production lines and restaurant operations, the stakes of early detection are incredibly high, leading to streamlined processes and increased success. It's crucial to highlight that prevention is better than inspection. Inspections can lead to unnecessary costs and do not completely eliminate defects, as some can slip through unnoticed. This process often shifts responsibility without truly resolving the issue, and may even create bottlenecks. Instead, focusing on prevention allows us to improve quality at the source, reducing overall costs related to failures. We can achieve this by developing efficient business processes through standardization and continuous improvement. For instance, a manufacturing company might implement a preventive maintenance program to ensure machines are running optimally, thus avoiding defects before they occur. In a software development team, adopting automated testing during the coding phase helps catch errors early, preventing costly fixes later. Another example is a restaurant that standardizes its recipes to maintain consistent quality and reduce food waste. This ultimately enhances customer satisfaction while minimizing losses. These proactive measures emphasize the importance of prevention over inspection. In a bustling city known for its innovative spirit, a small manufacturing company found itself grappling with rising operational costs. One day, during a strategy meeting, their eager operations manager, Ali the Nonya, unveiled an intriguing concept she had come across: the 1-10-100 rule. This simple yet powerful principle highlighted the importance of investing in preventive measures to avoid larger costs down the line. Ali the Nonya stood before her team, her visual aid illuminating the room. The pyramid diagram depicted 3 costs: prevention, correction and failure. It explained that for every $1 spent on prevention, the company could save $10 on correction costs and a staggering $100 on failure costs. Think about it, she said, her eyes bright with enthusiasm. If we invest just a little in preventing issues now, we can avoid far greater expenses later. If you enjoyed this content, please consider liking and subscribing. Thank you.